MVP Software Solutions, QA for Startups. This seminar addresses some of the issues that QA poses for startup companies or small companies and attempts to answer those questions in a way that will make them willing or interested in adopting QA. MVP Software Solutions has a lot of experience with varying companies and various sizes of companies. These are listed on this slide, the following slide, and the third slide following, which shows you companies for which we have provided presentations or training services. In addressing QA with startups or small organizations, we tend to run into the same questions or the same problems. They say they have no time for quality assurance. They have no funds for quality assurance. And everyone, particularly in small companies, knows all about the product. So everybody can test, everybody can develop, everybody can sell, everybody can support. And a lot of these are true at the beginning. It's not always true as we get to what we call the tipping point. Other things that come up is our testing has worked well to this point. So we're good now. We've always had successful testing in the past. But at some point you may encounter what we call a tipping point, where the testing may not be successful and then you start to scramble. Or we're too small to worry about it. And we're too small to be worried about by the organizations that worry about QA. For instance, our product may be quite small and only out to a limited number of people. Well, again, we hope obviously at some point it will go out to many more people. When we reach that tipping point where it suddenly takes off, we need to be ready for it. The last two that come up is that it's not worth the cost. Is it going to return a positive ROI to the organization? Or we have no long-term worries until we hit the tipping point. Again, this may or may not be true, but at this stage that's the answer we sometimes get. First thing we want to do is define three terms. Quality assurance is not equal to quality control, which is not equal to software testing. The three of these are not the same term, despite the fact that they are quite often used in the same way. So in order to make clear what each of these is, we're going to look at the following few slides. Quality assurance is working on the processes, fixing the processes, and it has a focus on defect prevention, and the key word there is defect prevention. We're preventing defects from occurring. Quality control, on the alternative, is viewed somewhat as a gatekeeper. They have checkpoints, they have checklists, they have in-process reviews. Can you give me all of these conditions prior to continuing on with this project? So they tend to be a gatekeeper. They have a checklist you must attain before you can move forward. And finally, software testing we define as active hands on the keyboard, creation and execution of test cases, and it is focused strongly and reactively on defect detection, i.e. we are trying to find defects that are already in the product and fix them, retest them, and ensure they're not there. This is a very reactive approach. Software testing, as we just said, finds defects that are already there. If they are not there, we would not have to find them, and that is the import of quality assurance. We want to eliminate them from occurring in the first place. If we could eliminate defects from occurring in the first place and not have to spend the time testing, finding, fixing, retesting, etc., we could do something else, which conceivably could be of substantially more value to the organization. Testing is not necessarily something you want to spend a lot of time on, but a lot of people do because they are worried about the defects that may be in the product. In general, if you do test, we have the following general testing guidelines. Testing shows the presence of defects. If I find one, there is a defect. So that means there was one there. I discovered it as a result of my testing, and now we have to do something about it. And there are a lot of choices, obviously, about what you do about it. You could choose to ignore it, you could choose to fix it, or you could choose to work around it. Exhaustive testing is impossible. We cannot test every possibility, every combination, every iteration of all the code. It simply cannot be done with a program of any size. Exhaustive testing simply exhausts your testers. General testing guidelines would indicate we do early testing, and we'll talk a little bit more about this in a couple of slides. You want to get it early testing early in the life cycle when it's easier to do. There is something that is called defect clustering that tends to occur in testing as well. If you have one defect in a particular area of the code, then we tend to have many defects in that same area. So they cluster in a certain area. Other parts of the code may be quite clean, and you may not have to worry about them. There is also what is called the pesticide paradox, which approximately translates as the more defects you find, the remaining ones become resistant to being found. They become resistant to the pesticide, as the statement is, and they cannot be found, and of course they lurk there and sometimes come up in production. Testing, of course, is context dependent. Whatever context we're in will drive the amount and the depth and everything else about the testing we do. We certainly have to work within the context of the software product in order to know what is important and what we need to test. We have to be careful not to fall into the absence of errors fallacy, i.e. just because we didn't find any errors doesn't mean there aren't any in there. We just didn't run a test that actually found one. This is a very, very dangerous fallacy, and a lot of people say, well, I ran all my test cases, none of them found a defect, therefore there are no defects. And frequently, of course, people desire that. Give me a defect-free program. Well, the absence of errors fallacy indicates that's not necessarily possible. Testing must be traceable to the requirements for the system. We certainly need something to base our testing on to make sure that we are testing against the same statement that the original program was built to. Whether or not that's a formal requirement or a user story or a use case, it doesn't really matter. As long as we can trace it to something and say, this test case checks this, we know we've done it. Defect data should be used to focus future efforts. This is a very strong piece of QA, and we'll discuss this a little later in the seminar. But defect data should be used to focus the future efforts of testing. If I find a lot of defects, as per defect clustering in one area, then I want to concentrate on that for future testing. There are probably more defects there. Testing should be done incrementally, from simple to more complex. We certainly want to dig out anything that is simple first, because they're probably going to affect a lot of items, and then worry about the more complex scenarios afterwards. We also want to do it incrementally over the life cycle of the development. And finally, testing tends to focus on exceptions, which is sometimes a concern. If you focus your entire testing effort on exceptions, you may not test the main line. You spent all your time testing the error conditions, you haven't actually tested whether the product works the way it is supposed to. Unfortunately, as a result of those guidelines and as a result of having to wait till there's actually code, software testing tends to be expensive, and it sometimes can be a waste of time and money. We spend a lot of time testing, we may or may not find critical defects, we may or may not find any defects, but we spent a lot of time doing that search. That can turn into a huge drain on corporate money. In addition, of course, as most of us are well aware, the cost of dealing with a defect goes up as the life cycle continues on. If you've got a defect at inception, it could be maybe zero cost. We won't have to fix it because we find it before we've even started the project. If we have it at requirements, it may cost a unit of 1. And please note, this is a logarithmic scale. That's why the line is straight. If it's at design level, it may cost 10 units of whatever, or dollars. If it's at code level, it may cost $100 to find it, fix it, and retest it. If it's in test, it may be 1,000. And if it's in production, it may be anything, including loss of the company. Certainly people have taken this statistic and worked it out, and they come up with figures that say how much their actual defects cost if they happen to get through to production. Some of them are very expensive, some of them are not so expensive. Quality control, which we mentioned a number of slides ago, is, as we said, checklists, gatekeeper activities, and in-process reviews. This can be very useful. Checklists have got a very, very good ROI. They're easy to make, can be generated and put on an Excel spreadsheet or something like that within minutes, and then you just use them every time you come to that point of the SDLC. All we have to worry about is whether the ROI on using quality control is positive. So if we find that the checklist tells us something that we would otherwise miss, or make sure we do every little step of the process, then that's probably a great ROI. Some of the gatekeeper activities will ensure that we get what we want at that point and can go forward and we're not missing stuff. Other things like in-process reviews or endpoint reviews are very, very useful and very, very cost effective in ensuring that everybody is trained and everybody has what they need, again, to move forward with the next step or the next stage. Quality control can be very cost effective. We just need to make sure that the ROI is positive. In general, that is not terribly difficult. So then the question comes up, why do we want quality assurance? Well, quality assurance is a holistic approach which looks at the entire process. We're not just looking at the test section, we're not just looking at the end of a phase or the end of a particular item. We are looking at the whole process and saying where is the most effective use of a quality assurance process. We look for places where quality control and software testing can be used most effectively. And again, that depends on the cost and the risk. Clearly, we want to use our software testing resources and expertise at a point where they can be very, very effective. We want to put our quality control checkpoints in at points where they're effective. We don't want to burden the whole project with endless quality control checkpoints. That's been done, and of course people just bog down in doing them and nothing moves. We want to make sure that we are using them where they have good positive effect on the rest of the project. We're looking in all cases for a positive ROI. So what do we do with quality assurance? Well, one of the things that we tend to follow is root cause analysis. Once we find a defect, and in this case we will have done some testing in order to find it, then we want to do what is called root cause analysis to find where it occurred and what was the root cause of it. We may find that this defect is all over the place, and correcting it once will fix it forevermore. There may be some point in the life cycle or somewhere back in the past where we basically incorporated this defect and repeated it everywhere. Root cause analysis will tell you that. It's going to be everywhere in the project. We fix it that time. We fix the process that created it, and then we never get it back again. This results in a better product. That defect is gone for all time. Other points we can use is the YY or Ishikawa diagram, sometimes called the fishbone diagram, and there's a picture of it on the slide here. And again, what we have here is the effect is usually off to the right there in that sort of semicircle, and then we ask for causes and subcauses of the subcauses until we find out what originated the error. It's a bit like root cause analysis, but it also brings in everything else that may have impacted that particular error. And that can be technical issues, or it can be resource issues or soft issues. It could be items like insufficient resources or incorrect communication, or it could be something technical. The machine can't do this, or the software can't do this. Whatever it is, this helps us find the root cause and fix it for all time going forward. The key point to quality assurance is process improvement. Because software is not the same on every project, we're not doing a bunch of widgets, we're not doing a bunch of production runs of the same thing, we cannot simply fix the actual item at that point. We have to fix the process that created the error. So in order to do this, we find the process that is in error, we fix the process so the error never recurs, and then that results in stopping the creation of time-wasting poor processes that can eat up cycles after cycles. If the process is broken, the results of that process will also be broken. No matter how well we follow it, they will be wrong as well. And that will continue on for the duration of the software and the duration of the life cycle. We'll have those errors on and on and on. Just to bring in a few of the quality pioneers here and say how they influenced quality assurance and why some of their contributions do apply to software, even though that is not where they started, we can look at W. Edwards Deming, who applied statistical techniques from the beginning. So he used statistical techniques. He was actually looking at manufacturing, but we want to use these in terms of the processes for software. This is how we carry this across to software quality assurance. So we're looking at how long the process takes, how many errors it may generate, how much you have to do before it to get ready or after it to fix up issues, and then we make decisions based on those facts. So we find out that our process is out of control, as the statement goes, and we want to bring it back into control. In terms of development processes for software, we may determine that the requirements process, much as it generates possibly excellent requirements, is effectively out of control and is endlessly being fixed in order to make it provide correct requirements. We need to fix that process. Maybe that requires us to bring in more resources or give more resources time, or simply look at the way they are being handled. It's quite possible that the way the requirements are being handled is wrong in some ways. Somebody's doing something to fix it so they are correct when we finally get there, but they're not getting there in a very efficient fashion. This brings statistical process control to software development and testing. It brings it into that field, even though the product that we're producing is unique every time. After all, if it wasn't unique, we could just copy the software that was already there. Joseph Juran, of course, had his quality trilogy of quality improvement, quality planning, and quality control. So he looked for where quality could be improved, he invoked quality planning, and then he used quality control to make sure that it had happened. He is bringing quality to software development with his quality trilogy. He's considered also to be one of the pioneers of software quality. The last one is Philip B. Crosby, who of course wrote the book Quality is Free, and his main argument, and how he got the title of course, was to incorporate the full costs of poor quality into the product. And we'll show a couple of slides based upon this in the next two sections, but basically saying that there are a lot more costs that we don't see that are involved in poor software quality, or in his case poor quality of the service, that we need to realize into the cost of the system and understand that those do make us operate at a loss rather than in profit. So what he really did was bring awareness of the full costs of defects to everybody's attention. If you just look at our picture here, we have the iceberg, and as you're well aware, of course, 90% of that iceberg is underneath the water. That's only the top 10% you're seeing there. The rest of it is under the water, and the same philosophy applies here. If we do get an error, we can see about deploying the fix, correcting the error, retesting the error, possibly retesting again. All of these lead to lost revenue. All of those we know take time, and we can see it taking time. It takes somebody time to deploy a fix, takes somebody time to correct the error, takes somebody time to retest the error and retest anything around it. What we don't tend to see, because it gets buried underneath the waterline, is the administration costs. Just simply extra time to record time, or to record the defect, or to record the incident, or to address it somewhere. Ongoing distrust of the company. Even though it's only one, as you're well aware with current social media, it's quite easy for people to report that one defect all throughout, and everybody knows that it happened. It's nice for other people, they can fix it, but equally it's a bit of a blot on the record. Potential lost business. A lot of people now assess products based on their rating on certain engines or certain sites, and of course if your product doesn't have a good rating, somebody won't pick it up. They simply won't use it. Opportunity cost from the fix time, of course, is time that we use to fix something rather than doing something new which might put us in a competitive position. Bad publicity on the market. Upset development and test personnel. Nobody likes going back to something they think is finished and having to redo it. And of course, business that we may have does not come back, so they may not continue to use the product. Even though they haven't got rid of it, they may simply phase it out over time, and we end up with the loss. These are sometimes the non-obvious costs. We don't have an easy way of tracking that. Somebody doesn't come back. Well, maybe they've gone out of business, maybe they've decided on another product, or maybe they're just simply using it and won't upgrade or pay the fee anymore. Whatever it is, they just sort of disappear, and that's not necessarily an obvious cost unless you go out and ask them. That said, of course, testing has its challenges. Even though we would like to put in quality assurance, we certainly have challenges with testing, and some of them are external interfaces where sometimes people didn't purchase things and it fell apart. We're always under threat. We have new tools, and we have the pervasiveness of software. It is everywhere. So we have current testing challenges. Having said that, why do we then test? Well, of course, we want to find the defects that are in the product. QA would tell you we want to avoid the defects, to reduce the risk inherent in computer systems. Again, you find the defects and remove them, that should reduce the risk. But equally, if we never had the defect in the first place, that definitely reduces the risk of that and other defects being missed. To satisfy the customer. Well, if we're testing and testing and testing to make sure the customer is satisfied, and that happens in some of our clients, then we may miss something. We may run out of time. They may not be satisfied with what we did. QA would tell you, figure out what the customer wants first, and then make sure you apply that to your development process. Prove that a program is good or no good. Strictly speaking, software testing won't do that for you. It will tell you that there are defects. It will tell you that your test cases ran, but it won't necessarily prove that the program is good or no good. Developers are unable to build defect-free software. Please keep in mind when you look at this sentence that obviously defect-free includes the fact that sometimes the requirements are wrong, and even though they build to the requirements, we still get a defective software. The user customer does not know what they want or does not tell us, so we test to see if we've done what we think is correct, but sometimes we're not representing the user properly. The development process is defective. This is crucial. If the development process is defective, then of course nothing will correct that problem. Because if I have a bug and I fix it with the same defective process, then I'm going to have something else wrong. If the development process itself is defective, we're going to have ongoing problems. To detect variations from a specification or expectation, as long as we have them, we can do that. Establishing confidence that the program does what it is supposed to do. Again, there are many paths through a program these days with many interfacing components. Doesn't necessarily prove what it's supposed to do in every case. Other factors, of course, that do affect software testing and sometimes have a detrimental effect are the people relationships within the organization. In general, testers are seen as somewhat negative, and if we have to do a lot of this, rather than just indicating the program is good because we built quality assurance into it, then we may have ongoing conflict. The scope of testing. How do we reduce that? Well, we ensure that more of the product is correct from the beginning, then we reduce the scope of testing as a result. Understanding lifecycle testing, it's not just a phase, it's not just a piece at the end, it is done throughout. Planning your work and working your plan is a standard, of course, for all SDLC, not just testing. And then finally, some testing constraints are some of the other things that impact us negatively when we do depend fully on testing to do our work. So our major impediments to QA. No time for quality assurance. Well, the reality is that quality assurance saves you time. If the defect isn't there in the first place, we don't have to find it. If we don't have to find it, we don't have to correct it. And if we don't have to correct it, we don't have to re-promote and do a stack of regression testing. This saves time. No funds for quality assurance. Well, in general, for most software, of course, time and funds are sort of two sides of the same coin. Less time means less funds. Everyone knows all about the product, so all can test. That's true when you're very small, but over time that knowledge disappears. Not everybody can keep the entire system in the mind and build a system boundary diagram for it. Everyone does not know everything about the product. The more we can get it correct from the beginning, the less you have to concentrate on in terms of what might be wrong. Our testing has worked well to this point, as far as we know. As far as we know it has worked well, doesn't mean somebody won't find something tomorrow that will blow it up. But at some point the testing ceases to work well because the product grows bigger than can be handled. At that point you're hitting a tipping point, and then things spiral out of control. We are too small to worry about. Well, that's possibly true, and if you stay that way, of course, then that may not be an issue. But at some point you may encounter a tipping point with that as well. You'll get big, and suddenly there will be people saying, well, how come this is not a good quality product? Not worth the cost? I think we've demonstrated that QA is cheaper than QC, or software testing. QA means that QC will pass without issue. QA means that software testing can concentrate on the more esoteric bugs and not on the common bugs, which won't be there. And if you have no long-term worries, maybe you should wait a little while and see if there is a tipping point. It all, of course, ends up coming down to risk and budget. What is the risk if something goes wrong, and how much budget can I put against that? The risk, of course, is the loss of the company, sometimes, particularly with startups and small companies. Some large bug may just mean you go out of business. Alternatively, the budget is what you can put against that. If you have any questions, please give us a call, 416-809-5539, or write to us at neil@nvp.ca. Thank you.